Okay, so guys, we're going to be learning some properties about integrals today. So this was a transition. I did my first year. I don't think we really need to worry about it. But so for the past week, though, we've been talking about Riemann sums, right? That's where you break up an area into shapes that you can just calculate the area with geometrically, but they're never exactly right? They're estimations. And what I was going to do is I was going to go to this website, but I'm not going to. And on that website, you can actually just kind of show an image where the rectangles get smaller and smaller, and it literally becomes the area under the curve. And that's when you actually get an actual integral at that point. So we're going to leave behind our estimations now. We're going to move into the world of actual areas under the curve, and that's this guy. Now, the lower limit represents your starting point. The upper limit represents your endpoint. The function here represents your line. And then the answer represents the area. Now, the area is always between the line and the x-axis, whether you're above or below, right? It's the area. And just remember, area below is a negative area. So that's the definite integral gives you the true area under a curve, unlike the Riemann sums. But actually, integration is basically just when you apply. We're not doing this because it takes too long and it's not very useful. But when you take the limit of the rectangle widths and limit approach 0, that's where you get the whole integral thing from in the first place. So that's where these come from. I'm not going to show you the process. It would take days to explain it, and it's not useful. So we're going to let it be. But now this is kind of important for today, so I don't know if you guys remember this or not, but while I'm chatting up here about it, if you want to write it down, you don't remember, you can. This is the fundamental theorem of calculus. It's how you find the area under the curve. So there is a difference between the little f here and the big F over here. The little f represents your original function. The big F represents the antiderivative. This represents area under the curve, but this is actually how we're going to end up calculating it. So what you do is say you had this. Say my function was 2x. Well, what we would do is we would integrate that. The integral of 2x is what? X squared. And we're going from 1 to 2. And so this represents little f. X squared represents big F. And what we do is we're going to plug in those limits, the upper limit minus the lower limit. And the answer that we get out of that represents the area. Okay? So that's the fundamental theorem of calculus. Now, geometrically, we can actually just solve this with geometry, by the way. I could graph this line, 2x, right? Y-intercept is 0 over 1 up 2. Pretty simple. It's going to look something like that, right? And we're going from 1 to 2. Well, that's just a trapezoid, isn't it? So we can find the area of that trapezoid and have our answer. But we already know it's going to come out to be 3, thanks to the fundamental theorem of calculus there. Okay? So just kind of reviewing some stuff that we already know, but kind of reining it back into calculus, because we've been doing pre-calculus to do calculus questions, finding area under a curve. We've been using geometry. Now we're transitioning back into calculus. So, all right. Interesting. All right. So here's our properties that we're going to be looking at for today. Want to make sure you guys don't just memorize them. Then hopefully they make sense to you. Can somebody tell me why this integral makes sense? Yeah. Beautiful. So he's seeing the picture in his head. So if this is my, I've got a function, right? I'm starting at A and I'm ending at A. I didn't go anywhere. You can't have area of a line. So this would come out to be 0. Good. So that one, pretty self-explanatory. Let's look at the next one there. I think the next one, what is this one? This one is interesting. So This one actually makes more sense without the geometry. I'll pull the geometry in a minute, but for now, let's think of it with the fundamental theorem of calculus. If I integrate little f, what do I get? Get big F. And since we're going from a to b, it's going to be big F of b minus a, right? Now over here, if I integrate this, it's going to be big F, right? But this time it's going to be what minus what? Yeah. And do you guys see how they're opposite signs? Like positive f of b, negative f of b, negative f of a, positive f of a. Well, if we put a negative in the front, now they're exactly the same. Right? So here's how we're going to think about this. We're going to think, okay, well, if you switch these limits, you just put a negative in the front and you get an equivalent expression. So if you switch the limits, you can put a negative in the front and you get an equivalent expression. Now let's think about the geometry of this, the geometric implications. So I've got a function here that's going from a to b, right? The area, let's say it comes out to be 10, right? From there to there. That's if I'm going this way. But if I'm going from b to a, now what's my area? Negative 10. Does that make sense? How about if I had this? No. First of all, what would the area be for this? It's going to be negative something, right? Because it's under the curve. But that's if I'm going this way. If I go this way, it switches the sign, right? So now it becomes a positive. So when you integrate going backwards, it changes the sign, basically. So there's your geometry of it. This one we've known for a long time. Back in Unit 2. Anytime you have a function like 3 ln of x dx, right? We've always just taken that constant and thrown it out to the front. That's old news. You can't do that with an x, like you can't do this. You can't take that x out and put it at, that's a no-no because you're integrating with respect to x, so that integration affects the x. It doesn't affect a constant, so you can just put the constant out. So we learned about that one a while ago. Here's another one. We learned that one a while ago as well. When you're integrating two functions that are being added or subtracted, that's just like taking the integral of each one separately. That's how we did problems like this. We just never really quite showed our work this way, but you know, if I asked you guys to do this, you know, you just take the integral of that and you take the integral of that. You just do each one separately. I just never took the time to write them as two separate integrals. Kind of pointless, but all right. This one is new. This one's kind of hard to see. So consider this integral here. It starts at a and it ends at b, right? So I've got a function and I'm integrating from a to b, and that represents the area under the curve, right? Now let's take a look at this other side over here. Now I'm looking at the same function. It's still f of x, but look at my limits are different. Now I'm going from a to c. Now let's assume that c is somewhere between a and b, right? So let's say c is right here. So that means I'm only going from here to here now. So it's like a piece of that area. But you notice where this one leaves off? This one leaves off at c, right? It stops at c. That's where this one picks up at, right? So this one picks up at c and ends at b. Yeah, so if you put the green area with the purple area, you get the original area, right? So that's it. So got to pay close attention to your limits on this problem. Where this one starts, that one will start at the same spot. Where this one ends, that one will end there. And those two integrals are connected at a common point. That puts them together in one giant area, right? And so that's another property we'll be looking at today. This one is kind of interesting. You could figure this out just doing the fundamental theorem of calculus pretty easily, but C, in this case, C represents a number, okay? So I just want to show you guys how to use it. If you ever have just a number here, like let's say I had 3, for instance, right? And then there's 2 here and 10 here. So according to this little property here, this number goes first, so that's going to be 3. And then what goes here is the difference of your limit, so 10 take away 2. And that's going to be 8. But instead of just memorizing that, I want you to actually understand why that works. So first of all, once again, you can do fundamental theorem of calculus. It's pretty easy. Like this would be 3x. If you integrate it right, plug in the 10, plug in the 2. However, I want you guys to think about this geometrically. This represents area, right? What's the function I'm integrating? The function is that guy. Yeah, oh, that's what you said. I thought you said 5. Okay, yeah, so it's 3. And that's a flat line, isn't it? Like that. And I'm going from what to what? So I only want this much of it. But what kind of shape is that? That's a rectangle. How do you find the area of a rectangle? Base times height. What is the base? 8, because it's 10 take away 2, right? What's the height? 3. This represents your height, and this represents your base. Base times height. So same thing here. This is your height. Let me rewrite all this. So this number here represents your height, and these two things put together, when you subtract them, represent your base. And so you're really just finding the area of a rectangle when you do that. So that's a geometric interpretation of it, but like I said, you could do it with fundamental theorem of calculus. That works too. But once again, that only works when this is a constant number. That's what gives you a rectangle, is you have that flat height there. All right. So now we're ready to use these properties. So let's go ahead and begin. I think I printed this for you. Now these integrals, guys, you could totally do these using the fundamental theorem of calculus. You could integrate this and get x cubed over 3. You can integrate this and get 2x squared, and then plug in the limits and subtract. It'll work, but that's not the point of today's exercise. The point of today's exercise is to see how well you can use these properties to solve problems instead of actually evaluating them. And in fact, there'll be some where I don't even tell you what the function is. So on those, you actually have to use the properties. You can't just evaluate it using old school methods. So here's the deal. I'm telling you what some of these integrals are already. So the integral of x squared from 0 to 6 is 72. Bless you. And I'm telling you the integral of x from 0 to 6 is 18. I'm telling you the integral of f from 0 to 3 is 10, and the integral of f from 3 to 6 is -8. And then I'm asking you to use those facts up there plus the properties we've learned to figure out what's up with this. So here's how we do it. Basically, we want to use our properties to rewrite these expressions so they look like these. And once they look like these, we can just replace those with the numbers they tell us that they are. Yeah, what's up, Birdster? What would you do first?
Well, number one, you can split it into the integral of x squared, which from 0 to 6, which we already know to be 72.
Good.
And then the integral, the integral of 4x from 0 to 6, which, as we know from property 3, you can just quadruple 18, and you'll get the answer.
Okay, good. So I'm going to say what he said again for you guys. So what he just did there is he applied property 4. Look at your papers there. Property 4 tells you that when you're integrating two things being added, you could just do each one separately, right? So he split those up. And then from there, he realized, well, this doesn't quite look like this, but it's close. What's the problem? It's got a 4 in there, right? What property has a number inside the integral with the function? That's property 3. What do we do with it? You just pull it out to the front. So if I do this, it's going to look like this. Now that I've pulled out that 4, I've got these two things isolated. So now I can just replace them with what I know them to be. What does this one equal? 72. And it's 4 times, what's the x one? 18. And once we go ahead and do the math, we're good. So that's the idea, is you want to somehow rewrite these integrals so they look like these up here using the properties. You're going to rewrite them. And once you get them to look like one of those up there, you just replace them with the values that they are, and you can simplify it. So 72 plus 4 times 18, 144. So go ahead and write down number 2 then. Thank you, Brody. Good job. All right. So looking at number 2, you guys, what property can we use here? We don't have anything up there with a 3. Property 6. I agree. Since you have just a constant here, right? That's property 6. That's a rectangle. What's the height of my rectangle? It's 3. What's the base of my rectangle? It's going to be 6, right? Because we're going from 0 to 6. So if you subtract those, you got that. Okay? So the final answer there would be 18. So number 3 is basically a hybrid of numbers 1 and 2. The first thing we're going to do is we're going to take the integral of each one separately, right? And then we're going to take out the constants. And then you're actually going to see another rectangle problem in there as well. So go ahead and write down number 3, and we'll do that one real quick. That's a 0 on the bottom there, in case you're wondering. All right, so first I'm going to apply property 4. I'm going to split them up like this. Is it minus or plus 4 after that? Thanks. And the next thing I'm going to do is this guy's already ready for a property. What property is that one? That's that property 6. That's that rectangle problem again, right? So it's going to be height times base. These guys aren't quite ready yet to be substituted because they have those constants in there, but we use property 3 to pull those constants out. So I'm going to put the 2 in the front. And I'm going to put the 5 in the front of this one. Oops. And now we can replace these with what we know them to be. This one was 22, and this one was 18. And that's going to be 24 now, and then from there we just simplify it all the way. We're done. 210. Moving on. Okay. Uh-oh. Well, that's interesting. I do. I'm having some issues. All right, next one. Okay, next one. So as for this guy here, That 6 can go to the front, right? We're almost good. But why doesn't this look like one of the ones that are up there? The limits are backwards, right? I'm allowed to switch those if I want to, so long as I do what? Put a negative in the front. So you can flip them if you want, just put a negative in the front. And so now we have negative 6 times 10, which is negative 60. All right, number 5 is the harder one. It is. All right. Before you guys write down number 5, like I already did. I want to make it look more like your student practice because my students struggled with this last block. I'm going to switch those around. Switch those around. Make it 6 to 0 instead. Okay. So for number 5, we've got f of x, so we know we're using these guys here, right? But none of those worked yet because I don't have anything that goes from 6 to 0. Now, first of all, we don't like having 6 on the bottom and 0 on the top because we like the bigger number on the top, don't we? All right, so I'm going to rewrite that. I could put the 6 on the top if I put a negative in the front. So let's do that first. Remember the fundamental theorem of calculus? It just reverses it.
Yeah, I'm just curious as to why you could do.
Why did I do that? There's different ways to do this one, but at some point you're going to have to flip.
Yeah.
And now why? Because look here, I'm going from smaller to bigger, right? Smaller to bigger, smaller to bigger. So you're gonna want to have that there too. All right. So, and that's just usually how integrals are anyway. We usually like to have the bigger one on top. It doesn't have to be that way, but that's normal. All right. So now this guy starts at 0, like this guy does, but he ends at 6, like this guy does. Yeah, good, good. So basically what I'm going to do then is I'm going to split this up. I'm going to say, okay, so I'm going from 0 to 3, but after that I'm going from 3 to 6. And that's that property, is it 5? Okay, now notice I still have the negative here on the outside, and I put brackets on the outside. So that's it. Since I'm going from 0 to 6, I can basically, if I just put these two together, then that gives me 0 to 6. If I go from 0 to 3 and then from 3 to 6, that's the same thing as just going from 0 to 6. Okay, so now we just have to plug in our stuff. We have 10 plus negative 8. So that's going to be 2 with a negative in the front. You end up with negative 2 as your answer. Okay. How about that last one there? What's the answer? 0, because the limits are the same on the top and bottom. So that's easy. All right, so most of the rest of the block is going to be you guys just practicing this, but I would like to get to some more maybe slightly confusing looking problems if we get some time, but we'll see. This is the basic idea though. All right. Sign. Some trig in there. All right. So there you guys go. For your student practice, we have these problems here. This one's negative 2. You can't really see the bottom number very good. And this one is also negative 2 in case you're wondering. But there you guys go. So try those problems there. You don't have to show every step like I was doing. I think that's nice to have in your notes for the first time you do it, just so your notes are helpful. But if you could just do it mentally, that's totally great. Just do it mentally. I think that's fine. So go ahead and do as many as you can the time we got. So for number 1, you guys, We know what the integral of x cubed is from -2 to 4. It's 60, right? But it's being multiplied by half, so that's 30. Okay? For number 2, we have a number there, and we have just a number. That's property 6. So we would do 7 multiplied by 5 minus 2. Now for the third one, I'm going to not show very much work, but I'll kind of walk you through it a little bit. So what's the integral of x cubed from -2 to 4? 60. Now what's the integral of x from -2 to 4? It's 6, but it's being multiplied by a -3, right? Now plus, now for this one over here, I'll write that one out for you. It looks like this, though, if you actually write it out. Well, that's another rectangle problem. We have our height being multiplied by the base. And this is where a lot of people were kind of missing it. It's minus a -2. So you end up with 60, take away 18 plus 6, which comes out to be, help me? 48? 48, thank you, that's right. Now, the next one, we should have ended up with -20. Now here's why. The first thing you guys should have done, you should have switched that 4 and -2. So if you switch those, you get this. Now, we do have integrals for f of x. They go from -2 to 0 and 0 to 4, but this one goes from -2 to 4. Well, it starts where this one does and it ends where this one does. That's the one where you add those two things together to get the total. If I go from -2 to 0 and then from 0 to 4, that's the same thing as going from -2 all the way up to 4. So basically, we have a negative on the outside because we flipped the integral, and then you're going to put these two integrals together. So the inside of the parentheses would make +20, but the negative on the outside makes it negative. Number 5 is just 0, no math needed. The limits are the same. Number 6, that integral is 60. This one's going to be -4 times the integral of x, which was 6. And then this last one, it's the same answer as this up here, the integral of f of x from -2 to 4. But this time, the limits are not switched, so it's a +20. And you end up with a total of 56 at the end. All right. I want to show you guys one more thing. We got a little bit of time left, and I would encourage you right now, because there are problems like this on your homework. It's not new, it's just a different way they're asking it. If I were you, I would take a picture of it, but just watch for now, and then if you guys want to write something down or take a picture, you can. But, so here's the deal. They're giving you two integrals up here. But they're going to ask you questions about integral pieces that you don't know. Like this one goes from -2 to 3, and this one goes from 1 to 3. But they're asking about -2 to 1, right? How do we do that? Well, the key is you start this problem off doing property 5. So look up here really quick with me. What is the lowest limit? -2. What is the greatest limit? 3. Right? Now, we're going to split that up into two things. The lowest limit was what again? -2. Where does that go? Top, bottom, left, or right? Bottom left. So the -2 goes here. It ends at 3. So where's that 3 going to go? Top right. Now, what are they connected with? The ones. So you're going to want to start these problems off like this, even though they don't tell you to do that. You'll start off like that. Now, what is this one? We know this one. What is it? And what's this one? The one we don't know is this, but can I solve for that? Just subtract on both sides, right? So if you minus the 8 on both sides, now we know that this thing here equals -4. After you know that, then you can solve any of these problems after that, because that's the only thing that makes it different. So they're going to give you a problem on your homework where they start off with two awkward ones, and it's your job to start off with property 5 to create a good equation that you can use to solve for the missing integral, so you could do the rest of the problem, okay? So you will see some problems like that. And that's it. So if you want to take a picture of it, go ahead. We ran out of time to actually do the exercises, but